Let's rock and roll, everybody. Because we are here to rock. All right. We are talking about NLP. That is an acronym for natural language processing, not neuro-linguistic programming. You might see that in psychology books or sales books or something like that. NLP stands for natural language processing. And this means that we're going to be working with words and text. That's all that means. Which begs the question, what on earth is a natural language? Anybody have an idea what a natural language is? And what other kinds of languages are there other than natural languages? Ryan?
Created and spoken by human beings.
Yeah, a language created and spoken and written by human beings. Yeah, absolutely. Absolutely the case. Jason Turner saying not code. Yeah, that's a pretty broad definition, but I would agree with Jason as well. The other kinds of languages out there, other than natural language. So natural language could be Spanglish, it could be English, it could be the King's English, it could be Castilian Spanish, it could be whatever dialect, whatever language human beings speak and communicate in this language. That's what natural means. The opposite of a natural language is a formal language. So the mirror opposite, or not mirror opposite, but the complete opposite of a natural language is a formal language. Anybody have an idea or an example of what a formal language might be? Andrew?
So I can speak to this because this is my background in Arabic.
Yeah.
There is a standardized version of Arabic that is used by the entirety of the Arab world. It's codified and standardized and formalized.
Really?
It is not spoken amongst people. The only time it's used is for educational or academic purposes. Nobody actually speaks them. In each country, they have their own dialects.
Right.
When you go on the street, if you were trying to speak MSA with people, they would understand you, but it would be awkward for them because they never usually speak with each other.
So this is new to me because based on my own definition of a formal language. So are the rules of this language completely unchangeable?
Yes. It's written in stone. It's because it's localized to a time when the Quran was revealed.
Okay.
So they say that is God's language, we must never change it.
Oh, okay. So people might start speaking that and then go into a local dialect.
Yes.
Okay.
They would never, if you started speaking the local dialect, it would not be considered modern standard. It wouldn't be considered
MSA.
Yeah.
Okay. That's what that acronym means. So it's a codified language, and you said it's written in stone.
Yes,
literally written in
essentially,
stone.
yes,
Yeah.
it's written and does not change, and the grammar cannot be changed.
That's the magic piece. The grammar can't change.
Right.
The grammar can't change, and I think this might qualify as a formal language. My linguistic exposure doesn't include Arabic, unfortunately. But yeah, formal languages, the grammar and the syntax will never ever change. So think math. Math is a formal language. Now, I say that knowing that math is super flexible and they invent new syntax all the freaking time. But established math, the last 2,000 years of math are codified. Yeah.
So when you say that, like math notation, like set logic.
Yeah. Yeah. Math notation, algebraic notation, musical notation, chemical notation, chemical reaction notation is a formal language. Yeah, anything where the grammar and essentially not necessarily the vocabulary, but the grammar and the rules will not change. So code, right? Code is a formal language. Any kind of logic notation, if you've seen like symbolic logic notation, it's a formal language. So natural language just means people language, right? Made my world a bigger place. Andrew, thank you for sharing that. And yeah, Jen is sharing Sanskrit, church talk, John Damal and Korean. Those are new to me too. But if I mean, there's thousands of years old, right? But if the rules of the language will never, ever change, not in a million years of humanity, that means it's a formal language. So natural language is people stuff. So when we talk about natural language processing, I want to be very clear that there's not one NLP algorithm or two NLP algorithms. It's not even one family of algorithms, kind of like how regression is a family of algorithms, classification is a family of algorithms. So NLP is not only one algorithm, it's not only a family of algorithms, it is any kind of tool set you bring to the party of processing and seeking to understand human language using programming. And so this could mean sentiment analysis, trying to figure out if some text is positive or negative, or if it's polarized, if there's opinions in it, or if it's fact-based. This could be and NLP has been around longer than we would call data science, right? Because people have been making chatbots for a very long time. Chatbots are NLP. Parsing reviews, product reviews is NLP. It's huge. So this is a big umbrella, and I promise you, we could spend 6 months in here, and it would be introductory to what exists in the world, right? Just like everything else, right? Just like every other topic that we cover in this whole CodeUp class, it can go infinitely deep. To draw a boundary around what we're going to be doing, we're going to be working with regular expressions. That's kind of a word algebra in programming languages. Regular expressions allow us to treat words as words and characters like symbolically, and work with those expressions. We're going to get into web scraping too. This is going to be a lot of fun. So tomorrow, I believe, today is regex. Tomorrow will be web scraping. You're going to get a little bit of a crash course in how the web works. I mean, we've talked about requests and responses, but we're going to talk about scraping websites and how HTML is stitched together. So you get a bit of a crash course in what our friends upstairs in the web dev courses are doing in HTML. It's basically a tree data structure, but navigating that tree is really interesting, and our tools are very powerful. Of course, we've got to prep our data always, and prepping the data with text, we need to normalize the text, right? Like remove plurals or account for different tenses, right? So if that's what we're focusing on. So we'll get deeper into that. Then we're going to get into exploration. The modeling component, again, modeling in NLP is not one algorithm or even one family of algorithms. You could do, there's regression, there's classification, there's clustering approaches in NLP. There's stuff like Markov chains for chatbots. The sky's the limit to get us something so we can move forward. We're going to do some classification with text. So supervised learning. There's supervised, there's unsupervised learning in NLP. Like I said, sky's the limit. And once we cover the basics, folks, we're gonna move into the project. And this will be a group project as well to get you all even more group work practice. And the project will be working with text from GitHub. So we'll actually be hitting GitHub to read READMEs about projects or libraries or initiatives, whether if they're data science projects or software projects, languages or libraries. We're going to scrape the READMEs, and then we're going to make classification around what language that README is about or what environment. So that one tool, that labeled classification, you can take this same tool and apply it to other labeled data sets, like author recognition. For example, like if you have a set of data where you know the author, you can then predict authors in the future on unseen data, right? Or we could do spam detection. That was the world's first like commercial grade NLP, spam detection in the 90s. So instead of just following human-based rules, The classification algorithm is looking for mathematical similarities between spam and not spam. Right? And we could do, like, if you've got the labels, you could do news or propaganda, right? And classify new text coming in. So this is cool stuff. And you know, I think if I had 6 months to work on just one thing in all of data science, I'd peel off a big old NLP project and go super deep. So let's jump in. NLP is not just ML. It's not just machine learning. NLP, even the underpinnings of NLP go back to good old-fashioned programming. But the magic of machine learning versus, not magic, but the thing that human beings feel is magic with machine learning goes back to this diagram on supervised ML, right? Classical programming takes in the rules and the data to give you answers. And this is how the first spam detection worked. Human beings said, oh, if there's free in the title, it's spam. That's a human-based rule, right? A human acknowledged rule. But with ML, we take in lots and lots of data and we provide answers, we provide labels. I mean, now we have more sophisticated spam filtering, and your spam button will unsubscribe you from the list and get that sender a bad rating and all kinds of other stuff. But 30, 40 years ago, email was a lot less sophisticated, but still ML was able to apply, knowing the answers to the data, those labels, figure out the rules to apply to new data coming in. And that's really what's so dang special about machine learning that human beings think is magical. It just kind of blows people away, right? In a way, it's doing what we've already done. But if you can automate the ineffable or automate something that only a human could do before, you've got capabilities, you've got a force multiplier. Cool. Y'all have all seen plenty of use cases of NLP. Autocorrect, right? Spell check are good old fashioned. I mean, those are 40, 35-year-old NLP projects. Things that are making huge waves right now is NLP researchers and practitioners giving voice to customers. So if you have enough employees to read customer reviews, that's great. But if you have thousands of customer reviews coming in a day, you need to know if they like you, they hate you, or what's going on. So extracting key phrases, going through telephone transcriptions, the sky's the limit. If you can turn something into text, you can then do NLP on it. Search and semantic search. So search engines use a heck of a lot of NLP, right? And knowledge management, discovery. One specific kind of family of models in that would be topic modeling. Given a bunch of text, what are they talking about? And so you can do topic modeling to figure out the topics, and that's getting rid of like pronouns and filler words and using some statistical methods or ML methods to figure out what the topics are. And so if you've got a body of text, you can figure out what are your customers talking about, and also determine the sentiment. Are they happy about what they're talking about? Are they fact-based about what they're talking about, or is it opinion-based, or are they upset about it? So our project and what our curriculum is going to cover is text classification. And this is pretty good bread and butter stuff. This is going to get you through a lot of cool NLP projects like sentiment analysis, spam detection, topic labeling, intent detection. Text classification is all supervised. So we do have to have either labeled data or some human beings on the team or somewhere who are doing a labeling process, right? We've got some friends over at TaskUs. TaskUs does some pretty cool work. They've got a lot of of data science talent and ML talent, especially in NLP, and they hire a lot of folks to read online content to moderate and look for abusive content or, yeah, you got a story?
I used to work there.
Oh, really?
I asked about that.
Oh, really? So you know 10,000 times more than I do, yeah.
I mean.
Am I hitting the mark?
It's correct.
Yeah, yeah. Were you on like content stuff?
Yeah, I did content moderation, and then I got to, they changed the title to client analyst to basically like QA.
Oh, yeah, yeah, yeah.
We use like the insights, make a little slide with the client.
Oh, that's cool. Hey, interesting.
Yeah.
I know, I know, I saw something that they sold a little bit of the company yesterday,
Oh, really?
but they're like always hiring.
Yeah.
Yeah, or they at least always have data science jobs open. Yeah, that's pretty cool.
That's actually what put me on this path.
Oh, really?
That was like what I was doing was like the really baby version of data science.
Right.
I kind of feel like insights, whatever.
Sure.
And I tried getting into the data science like branch that they had,
Right.
and didn't quite work out because I didn't have the experience.
That's unfortunate.
But that's why
Yeah. I'm glad you're here. I'm glad you're here. Yeah. I'm spacing on the guy's name. He flew down from like either Philly or Boston or something. And he was talking, gentleman from TaskUs, I think head of data science, was talking about an initiative to try and up-level internal people.
Yeah.
Yeah. But anyway, I'm glad you're here. I'm glad you're here. So yeah, that's pretty cool stuff in small world. Yeah, TaskUs is the company. Pretty large employer in San Antonio, actually. They're out of the Philippines, company owned in the Philippines, but. So yeah, that's really interesting because my understanding is there's people labeling the data and there's people using those labels, not to put the people labelers out of a job, but to automate as much as possible is my understanding. Yeah, that's cool. That's cool. Some other things that you might do in an NLP space is topic modeling. And this is unsupervised. Think of this kind of as almost like a type of clustering. And it's not exactly clustering, like you're not going to throw k-means or dbScan at text because it's not numbers. But you're trying to figure out what topics exist if you don't have the time or if you don't have a whole bunch of employees who are reading this stuff, figure out what the topics are. So our data science pipeline doesn't change too much. We take in, instead of spreadsheets or databases, we're going to take in text documents. And that text could be on a web page. It could be a plain text file on a computer. It could be text in a database, whatever, or an API. And we're going to have to do some text pre-processing because computers don't do well with or at least algorithms don't do well with letters. And this whole class I've been sharing, we can't do ML on strings. So we do have to do some pre-processing. That's going to be a lot of text normalization. And we will explore the text. So our EDA is on plain text, but where we really turn the text into numbers, think of it kind of like encoding. It's basically encoding is we're going to turn that text into numbers, and then we can do modeling or data mining and send that into algorithms. Okay. And then once you've got a model, then you can deploy that model, update that model with new bodies of text come in. Because if you've trained an algorithm on last year's reviews, you don't want it to have drift between new comments coming in. So That brings us to the wrangle, right? I'm going to introduce a new word. If you haven't heard this before, the word is corpus, and I'm not talking Corpus Christi. I am talking about just your body of text. And that body of text could be a sentence, it could be a paragraph, it could be a book, it could be a whole bunch of books. Your corpus could be an entire library, potentially. The GPT-3 library, their corpus was as much of the internet as they could fit, as those researchers could fit into memory. Yeah, if you really are want to be on the cutting edge of NLP, GPT-3, and it's kind of scary. This is the model that, did y'all hear about that bonehead over at Google that said that the AI was self-aware? Yeah, well, humans are fueled by randomness, right? It's one thing if like your great uncle Bob says, you know, some algorithm self-aware, but if somebody knows better says it is, they need to get their head checked, right? But yeah, the larger your corpus is, the more real any kind of output or insight from that model will feel to us. And we are so tricked by randomness. If your corpus is Bart Simpson quotes, then if you generate any text out of that, you're going to sound like Bart Simpson. But if your corpus is like all of internet traffic for a day, you're going to sound like the world, right? So we need to be mindful of that. Like if your corpus is all of the J.K. Rowling books, for example, then that's the limit of that, right? So GPT-3 is a huge, huge data set. It's gigantic. And that's some bleeding edge stuff. We are chaos machines. Wow, that's a pretty heavy metaphysics this early in the morning for me. We do want to convert to sentences if necessary, or if that helps us, and then we're going to normalize the text. And there's not a one size fits all for normalization. And at this point in the game, this first bullet point says lowercase all the text. Well, some NLP algorithms try to pay attention to uppercase to see if somebody's shouting. By and large, though, most of the time you want to lowercase things because we don't want the letters for like code up to be different than code, right? Like the letters are actually different numbers underneath the hood, like a capital C and a lowercase c are different numbers underneath the hood in the character key lookup. Unfortunately for our friends using the Roman alphabet, but with accents, part of normalization might mean removing accents, removing some special characters. We might want, again, this is not all or nothing, we might want to remove numbers, or if we're just focused on sentiment. And punctuation, although keeping in mind, exclamation points might mean something emphatic. So this isn't a one size fits all kind of a situation. But generally, this is what normalization means when folks are talking about it. You might make a strategic decision to remove special characters and accents, but keep things uppercase, if like the whole word is uppercase. Like this service rocks, or doesn't. Andrew?
I'm sure we'll get into this, just curious if you can 5 seconds. You say convert sentences, and then we're going to remove punctuation. So does it separate those sentences out in like, yes, individual cells of a data frame? Or how does it know that they're sentences if there's no longer any punctuation?
Good question. Good question. Oh, the weasel answer is it depends. But what is it going to depend on is the level of what you want each row in your database to represent.
Okay.
Right? If we're tracking dialogue back and forth, we need to have the label of who said what. So each row will be Andrew said, Ryan said, Andrew said, right? But if we're doing, say like a news article, in that case, the sentence piece doesn't matter. It's just one big run-on sentence once you lose the punctuation.
Yeah. Okay.
I'm gonna check. Yeah, great question. The question was, had to do with, well, if we convert everything to sentences, don't we just end up with another big run-on sentence? And to repeat the answer, Jen, it depends on if what you're trying to track is like line by line dialogue, perhaps, or if you have one author for everything, it could just be one big honkin', or even just a book, right? If you had a book with one author, that whole book could be one string, and that would be one record in the row. And then the second row could be another book from a different author where the entire book is one string. Just like everything else in data science, right? I give y'all license to say it depends, and I give you my professional encouragement, hopefully not admonishment, but encouragement to always follow up with what that depends on and what the trade-offs are and in what case. And if you don't know, just say you don't know. We're also going to do something called, this is an either or operation, either stemming or lemmatizing words. And so we'll get into the differences here. Stemming is dropping prefixes or suffixes to try and get at the root of a word. It's very computationally easy because it's just following a set of rules, like a simple set of rules. Lemmatizing is a bit more computationally complex, but lemmatizing is trying to account for tense. So ran, runs, running to get to the root run. Stemming is not that sharp. So, but it's an either or. So like if you're dealing with so much text that, you know, you've got to watch out for your hosting bill or it can't fit on a computer, it's stemming. Lemmatizing, if you've got a little more time, your corpus isn't quite so large, you probably want to account for tense and things like that. Cool. We're coming around the bend on the review here. We'll introduce in the prep a little more fully this idea of tokenizing and breaking our text into tokens, breaking and getting our linguistic units into words. And we might even be very interested in n-grams, such as 2 words together, or 3 words together, or 4 words together. That's what the n means. So data science is a bigram, right? Code-up data science is a trigram. And so you can filter through your corpus and look for, basically give me all the bigrams. And if you've removed all of the filler words, your bigrams, some of them might be really interesting. You know, I'm realizing, especially for text that y'all are generating right now, like resume text and LinkedIn text and cover letters, stuff like that. There's NLP being run on resumes all day, every day, looking for n-grams, looking for data science as a bigram, right? And looking for doing topic modeling, things like that. Something that is pretty big in NLP, we're not going to get into this level of it, is part of speech tagging. And there's libraries for this. Things like Hugging Face is like GitHub for NLP. It's just NLP craziness. It's awesome. Tools like Spacey, which I would love to include in the next NLP updates. So tagging parts of speech. And also chunking and a big one is named entity extracting locations, extracting names, extracting proper nouns. So even if the algorithm doesn't know that a string is a proper noun, because it's not part of a dictionary, basically, there's ways of pulling that out. So named entities could be things like just proper nouns, not just persons, places, or things, but proper nouns, just ideas as well. Let's see, bag of words, CFIDF, vocabulary. Okay, cool. I need to introduce y'all to the idea of vectorization. And vectorization is basically like a histogram of word counts. So you treat each sentence like a separate document with vectorization, and you make a list of all of the words in all the documents. And then you create vectors, and the vectors are just lists. So don't freak out. I know it's a math word, but it just means a list. So if we've got the text, it was the best of times, it was the worst of times, it was the age of wisdom, it was the age of foolishness. We get the first thing that we'll do with vectorization. And again, you don't need to do this manually, but this is explaining what vectorization is. We get the dictionary of all unique words. That's the first step. So it's the best of times, worst, age, wisdom, foolishness, because it's not counting the repetitions here in the dictionary. So that's just basically taking the string and running .unique on the words, right? So taking a string, turning it into a list of strings, and then running unique on it. And then we see here we have an encoding. It was the best of times. See how we have it was the best of times. So it just so happens that first sentence, all of its unique words populated the first couple of indices of that dictionary, but the word foolishness was not there. The word wisdom was not on the first line. Age was not on the first line, and worst was not on the first line. And so we're doing basically counts per word of occurrences. So it was the age of foolishness. Is foolishness turned on or off? It's turned on. That's vectorization in a nutshell. The easiest thing to do once you have word counts and this kind of vectorization is do something called bag of words. And this is kind of a naive approach. I mean, not naive in a bad way, but naive in like, you could build this without a library. You just build this in base Python, bag of words, right? You're just counting things and doing a frequency count. Bag of words and just this frequency of word count. This was how some of the first search engines were determining topics of websites. So I don't know if anybody was trying to do search engine optimization, before 2000, you could just jam a bunch of crap in your HTML and you'd repeat words, and you would rise in the rankings because it saw the repetition as important. So bag of words is easily hackable. It's easily gameable, right? All you got to do is repeat things. So that's what I mean naive. It's easy to build, but it's not that sophisticated. Some ways of getting a little more sophistication statistically here, or at least algebraically, is the normalized count occurrence. So we take our term frequency, and that's our count of keywords in a given document, and we divide that by the count of all words in the document. So we get percentages by each. Now that's still pretty naive. Now something that's a little more powerful is this thing called term frequency inverse document frequency. And we're going to work with this. The idea here is based on the approach that high frequency doesn't provide a lot of information gain. Like if the word the is everywhere, is your book about the word the? No. So the idea is that rare words contribute weights to the model with TF-IDF. So check this out. The idea of TF-IDF, the term frequency, that's the bag of words, right? Term frequency for a given word, that's the numerator. The denominator is the inverse of how frequent that word shows up in the entire document, the entire corpus, not just in that one page or that one blog post or text message. So what this gives us is word importance increases when that term is very frequent on one blog post, for example. But if it's that one word is not frequent across every blog post, that tells you that first blog post is about Python, right? And this term frequency, inverse document frequency algorithm just because of how humans work, this really pans out regardless of language, regardless of spoken language. This works in Romance languages, this works in Eastern Asian languages, just because if your one document is about topic A and the rest of your documents don't talk about topic A, it means your first document's about topic A. Doesn't really matter if it's in Mandarin or Spanish or English or what, just because people. So this is less naive. It's still pretty simple. And we're going to use the TF-IDF factorizer to do the arithmetic for us, to do all the dividing for us.
Question on that real quick.
Yeah. Go ahead, Kate.
So I guess when you look at whatever your inverse document is it always like of the same type of what you're looking at? Or is there some library that is sometimes used in whatever language? So say I'm doing English and I want to see term frequency and I want just some generic inverse document that's common to the English language. Is that a thing? I don't know. You know what I mean?
I think I understand what she's saying.
Yeah, go ahead, Andy.
She doesn't have a corpus of documents, she has one document. So she wants to compare that to the broad language. Is there some sort of broad thing that we say this is the
Oh, I gotcha.
frequency for the language?
The term frequency for the language would be GPT-3 or GPT-2, its predecessor. To have all of a corpus of things written in English, you'd have to have that corpus. There are corpora that do that, that attempt to do that, right?
So there is some standard out there that I could maybe grab this, however many character document as a proxy for a corpus.
Short answer, yes. The long answer is all the buts and caveats. All the buts and caveats would be, where did that corpus come from? Is that corpus from the New York Times? Is that corpus like the great works of classical literature in English? Like your corpus matters a lot. But you can find pre-built corpora if that's what you're asking.
Cool, thanks.
Yeah. Mindy, go ahead.
The norm equals 12 is 12.
Oh, it's a L2. The norm is a measure of basically distance of vectors. So I'll give you an example of a norm. Say we have, let me make sure our folks at home can see the board here. So if you have 2 points here and here, an L1 norm, I don't want to get too mathy, but it's a lot of fun. An L1 norm is the distance X plus the distance Y. So this is actually, this is Manhattan distance or taxi cab distance. So this is the distance between 2 points. This is a vector of 2 points, 2 dimensions, right? And our distance between A and B is length plus X plus Y, right? Now that L2 norm is Euclidean. Sorry, I can spell, I promise, Euclid. Euclidean distance. And this is the hypotenuse. Euclidean distance, or an L2 norm, is as the crow flies. And I say as the crow flies because that evokes an idea of three-dimensional space as well. And these vectors are however many freaking dimensions. But an L2 norm is the shortest distance, Euclidean distance.
If you don't want to get into it now, that's fine. I'm just curious, like thinking what would be best and what. I'm just.
I don't see any reason why we would want to use a Manhattan distance. There's other measures of distance. Oh man.
Would it default to L1? I mean,
Let's check. It should. I wouldn't be surprised if it defaults to L2. Yeah, it defaults to L2.
okay.
So that's Euclidean distance. So that's the hypotenuse. That's always the shortest distance between 2 points, even in 3 space or 4 space or 5 space. Our other norms, our other measures of distance, let's see what we have here.
Example, I think,
Yeah, the L1 that's the sum of the absolute values of the vector elements. I haven't seen a compelling reason to use L1, but really, I'm getting so jazzed up. All norm is a way of measuring distance. So Euclidean distance is like measuring blocks. There's also this concept, and it's not part of this vectorizer, but it's part of just NLP in general, called the Liebenstein distance. And so if we had the word Blanco road, and we had a misspelling of Blanco road. So let's say these are all lists, space character, right? The Liebenstein distance between these two, 1, between those two strings. And if we didn't have the road there, our Liebenstein distance would be 3. So this is another measure. This is a non-geometric way of measuring distance between words. And this allows, Liebenstein distance allows us for like fuzzy search. And when you misspell something in a Google search and it comes up, yeah.
L2 would just be that difference squared, or the square root of that difference, or the sum of those differences. So it'd be like the square root of 3.
The square root of the sum of the squares. It's the hypotenuse.
Since it's all ones in the vector, it's just the square root of the sum.
Oh, yeah. True story. Yep. Cool. Yeah, Liebenstein distance is pretty powerful. Y'all have all benefited from things like this and Google search and stuff like that.
Yeah, it's funny, over the years, like, as I'm typing things in, it can be more and more wrong.
Yeah.
And still get to the right space.
Right. Like, pre-2000, the search engine wouldn't autocorrect for you. Yeah.
I mean, it's gotten bad to the point where like, people are getting worse at spelling. It's like, just put
Right.
something close to it.
Or the spelling help on a search is so helpful that if I looked for something specific that's rare, that's more rare than how common people misspell something. Have you ever noticed that as well? The other side, yeah. Remote folks, did y'all catch that Liebenstein distance, the distance between characters? Like Blanco versus Blanco, and the distance is, or the Liebenstein distance is 1, because it's 1 character difference. And that could be for the absence of a character as well between 2 strings. Cool, I get jazzed up about this stuff. So word embedding is another way of representing a document vocabulary that gives you opportunity for semantic or syntactic similarity detection, relation between other words. One of the more common tools for this is a library called Word2Vec, Word2Vector. And we can do bag of words with that, or skipgrams. Now, skipgrams are kind of a trip. We talked about bigrams, where you have 2 words right next to each other, or a trigram or a quadgram. A skipgram skips words. Because of how language works, we might have a dependent clause that describes some other term. So the skipgram is hopping around that sentence. Pretty wild. So there's a whole bunch of vocabulary that we can introduce now. We're not going to get into every piece of this. Entities and named entity identification. Our curriculum is not going to cover named entity extraction, but there's libraries for that. If I had to do some NLTK is one of the libraries that we're going to use. It has some named entity stuff. I'm almost 100% sure on Spacey does for sure. Hugging Face has a lot. Stemming and lemmatization are ways of getting to the root. Tokenization is breaking text up into linguistic units like words or engrams. A document could be, all a document is a single observation. So if we're talking text messages, a document is one text message. If we're talking news articles, like all of the New York Times, a document is one single article, right? And the corpus would be all of those documents together. So really what the document is up to you. If it's dialogue, each document is going to be a sentence per person, per Horatio, right? Or Hamlet, right? If you're talking about, if you're looking at like a book series, a document could be one chapter. If you define it that way, it's really kind of up to you. You could define one row as a chapter or one row as one whole book if you wanted to compare different books. Like maybe you wanted to see Wheel of Time series, how different the last Wheel of Time book was due to the extra author, right? Compared to the others, your book would be a document. And we've got a little diagram of part of speech tagging. So. Because natural language is weird. I ate the spaghetti with chopsticks versus I ate the spaghetti with meatballs. Did you eat the chopsticks? Did you put meatballs on your fingers? This is why formal language needs to actually be written in stone, like math or code. I mean, even if we spoke in this, you said it was. What was the type of Arabic called again? Modern standard Arabic. Yeah. Even if you misspoke in modern standard Arabic, an Arabic speaker would still, it would sound funny, but they could roll with you, right? Math or programming, nothing works. Yeah, like you get syntax errors in programming.
Yeah, well, I guess the difference would be is like if you as a person were analyzing something that was written correctly, you'd still be able to interpret it the error.
Yes.
That's the difference.
Yes. Yeah. There's an interpretability.
Just what I want to make, so is it, and goes my partner being an speaker, but is it like instead of saying ballast and D, would that be like the equivalent? Because
it's older. We're talking the Quran, so 700 AD.
Yeah.
Ballast and D is from like the 1400s.
Oh, okay.
Further.
I'm wondering if that's like just from the equivalent.
A very simplistic idea would be that, yeah.
Yeah, very simplistic, like that frame, okay, for how to think about why it's, why it's understandable.
It would be the grammar of the King James Bible locked in place, and that's the only way that we would read and write to each other.
I think what's interesting though is like, it's still really used, like all the news and stuff is in it. So you kind of gotta.
Oh, wow. Yeah, that makes sense. That crosses more cultural barriers for a religion that's so spread across the planet. Yeah.
Yeah, but it seems like for something like this, like you would maybe like MSA for something or not, like.
Oh yeah. You could do NLP on MSA or any other written or spoken language.
I thought a really cool project would be like the Olympians, like analyze the entirety of the Quran, each surah individually, to see the differences between the surahs, because they say it was all, written by God.
Right.
And see if there are stylistic differences between each one, to see what the differences might be.
We're gonna get a lot more, all like that. Something like that, but.
These are really interesting challenges. And I think, I mean, definitely a purist would say that even a spoken language is, or a written language is set in stone isn't a formal language because it's still a people language, not a notation structure like math or code. But I've enjoyed the discussion. So this is awesome. That's the intro. Like I can't fit every possible topic in NLP to y'all in one intro. If you really want to go above and beyond and super deep, Hugging Face is super powerful. Kate brought up the idea of how do you, is there a standard? And the answer is there's lots of different corpora. Hugging Face has corpora. It also has models that are trained on different corpora and models that are trained for different specific purposes. This is above and beyond what's in the curriculum, but I do want to share with you y'all Hugging Face and Spacey. And between Hugging Face and Spacey, you can just blow the doors off. It's wild. And Hugging Face just has a huge repository. If you want pre-built models, let's see, there's 58,000 pre-built NLP models on Hugging Face. Let's look for one on, oh, there's not, oh, there we go. Modern Arabic. I don't see a specific model in there. We could say,
You just search Arabic, there's something.
yeah, almost a couple hundred Arabic models. We could plug in Greek, couple hundred, almost 200 Greek models. If we wanted to do author detection. I guess the detection, they got to work on their own search here with NLP projects, because there's probably some author detection in there somewhere.
So for author, or are they just looking at like language that the author generally uses and?
Yeah. Yeah, and you can do automated plagiarism detection with that, and gosh, even in like a legal sense, if there was an email that said it came from the CEO, but you do some author detection, it's statistically dissimilar from other emails. You never know. Like maybe a shadow author wrote that or something like that. Yeah, pretty wild. So yeah, Spacey and Hugging Face are some next level steps. I think if I had a magic wand, I'd have some Spacey curriculum for y'all. But I'm happy with what we have. It's going to get you airborne. But that's really good stuff. Yeah, find out if Shakespeare really did. Yes, you can do that. Morse code. I would say that I know Morse code as far as how to encode letters, but if there's any other syntax to Morse code, I wouldn't be surprised if there's shorthand, or if you've got to read in between the lines. That's not a formal language. If you're ever reading between the lines, that's a human language. That's a natural language, right? Like you don't need to hear the S on an SOS to know that it's an SOS, right? A lot of the times you hear the first two characters and you get your butt in gear, right? Cool. That's the intro to NLP, folks. Great discussion. Let's take a little break. We'll come back at 10:20, and then we're going to rock and roll with some regular expressions. 10:20, folks.